Welcome! In this session, we'll explore problem number 504, titled Base 7. This problem challenges us to convert a given integer into its base 7 representation, leveraging our knowledge of number systems and modular arithmetic. Let's dive into the details and analyze the solution approaches. In this problem, we need to convert a given integer into its base 7 representation, which is returned as a string. For example, if the input number is 100, the output should be 202. Let's break this down. When we divide 100 by 7, we get a quotient of 14 and a remainder of 2. This remainder represents the least significant digit in the base 7 representation. The process doesn't stop here though, because we now need to further divide the quotient to get the next digits. Continuing the calculation from the previous example, we take the quotient of 14 and divide it by 7. This gives us a new quotient of 2 and another remainder of 0. Finally, we divide 2 by 7, which results in a quotient of 0 and a remainder of 2. When we read the remainders from bottom to top, we get 202, which is the base 7 representation of 100. Now, looking at another example, if the input is -7, we follow a similar process. First, we ignore the negative sign and treat the number as 7. Dividing 7 by 7 gives a quotient of 1 and a remainder of 0. Dividing 1 by 7 gives a quotient of 0 and a remainder of 1. Reading the remainders bottom to top gives 10, and finally, we reapply the negative sign to get -10. Next, let's consider the case where the input is 0. For this, the base 7 representation is simply 0, as there are no calculations required. Now, let's look at the constraints for this problem. The input integer, number, is guaranteed to be between -10 million and 10 million. The output must always be a string representing the base 7 conversion. Additionally, both positive and negative integers must be handled correctly. Special care should be taken for the input 0, as the output in this case will always be the string 0. Finally, there are a few key edge cases to keep in mind. For the 0 case, if the input number is 0, the result should directly be 0 without any additional calculations. For negative numbers, the base 7 conversion should be computed for the absolute value of the number first, and then the negative sign should be prepended to the result. Additionally, when handling very large or very small numbers, like -10 million or 10 million, the solution must ensure it can process these extreme values correctly within the given constraints. Each of these considerations is critical to ensure the solution is robust and handles all possible inputs. To solve the base 7 conversion problem, we can consider a brute force approach that involves manual division and modulo operations. The key intuition here is that base 7 representation is achieved by repeatedly dividing the number by 7 and keeping track of the remainders. This process mimics the way numbers are converted into different bases by hand. First, we handle the edge case where the number is 0, as its base 7 representation is simply 0. Next, we determine if the number is negative and convert it to its absolute value for simplicity during calculations. Using a loop, we divide the number by 7 repeatedly, storing the remainders at each step. Since the remainders represent digits in reverse order, we reverse the sequence at the end to get the correct base 7 representation. If the original number was negative, we prepend a dash to the result. This approach is straightforward and easy to implement but requires careful handling of the sign and reversing the digits. In terms of complexity, the time required is proportional to the logarithm of the number in base 7, while the space complexity is also determined by the storage of remainders, making both O log_7 number. While simple, this approach has trade-offs, including the need for manual digit reversal and sign handling, which can add slight overhead to the implementation. An alternative to the brute force method is the string-based approach, which can use either recursion or iteration to construct the base 7 string directly. The intuition here is to avoid manually managing remainders and instead build the result as a string during the conversion process. In the recursive version, we handle the edge case for 0, and if the number is negative, we prepend a dash and recurse on its absolute value. For each recursive call, we calculate the base 7 representation as the result of the recursive call on the quotient, combined with the current remainder. This continues until the base case is reached. The iterative version is similar in concept to the brute force method, but instead of storing and reversing remainders, it constructs the result string directly. Both recursive and iterative implementations have a time complexity of O log_7 number, since the number of divisions is proportional to the logarithm of the input in base 7. The recursive method has a space complexity of O log_7 number, due to the call stack, while the iterative version is more space efficient with O additional memory. While recursion provides an elegant solution, it involves extra memory costs, making the iterative version a more practical choice in environments with strict resource constraints. For this problem, we select the iterative brute force approach as the optimal strategy due to its simplicity, efficiency, and minimal memory usage. By iteratively performing manual division and modulo operations, we can directly construct the base 7 string without relying on recursion, which helps avoid the overhead of function calls. The process naturally aligns with the iterative nature of base conversion. In this approach, reversing the remainders is the most straightforward way to obtain the correct order of the digits. Additionally, by isolating the handling of the number's sign, we simplify the algorithm further, making it cleaner and easier to debug. The algorithm begins by explicitly handling the zero case. Next, we use a flag to track whether the number is negative and operate on its absolute value. We then repeatedly divide the number by 7, storing the remainders. After collecting all the remainders, we reverse them and construct the result string. Finally, if the original number was negative, we prepend a dash to the result. This method keeps the implementation concise while maintaining both efficiency and robustness. Analyzing the complexity of this approach, the time complexity is O log_7 number, as the number of divisions is proportional to the logarithm of the input in base 7. The space complexity is also O log_7 number, due to the storage of remainders during the iterative process. This iterative method is chosen over alternatives for several reasons. It is more space efficient than recursion, as it avoids the extra memory costs associated with the call stack and eliminates the risk of stack overflow for large inputs. Additionally, the iterative method is straightforward to implement and debug, making it an excellent choice for interviews and production scenarios. Comparing the iterative brute force approach with other methods, it is easier to understand and avoids the memory overhead of recursion. Constructing the result directly as a string is also more efficient than manipulating intermediate strings or relying on recursive calls. While recursion may appear more elegant, the iterative approach is more robust and scalable, striking the right balance between simplicity, efficiency, and practicality for this problem. To solve the problem of converting a decimal number into its base 7 representation, we need to break it down into clear, structured steps. First, let's understand what base 7 means. In base 7, each digit represents powers of 7, starting from 7 to the power of 0 at the rightmost position. For example, the number 100 in base 10 is represented as 202 in base 7 because it breaks down into 2 times 7 squared, plus 0 times 7 to the power of 1, plus 2 times 7 to the power of 0. To compute this systematically, we repeatedly divide the number by 7, taking note of the remainders, which become the digits of the base 7 representation. These remainders are recorded from least significant to most significant, meaning we eventually reverse their order to form the final result. To start, we initialize a few variables, the input number n, and empty list digits to hold our remainders, and a way to track the sign of the number, since negative numbers will require special handling. Additionally, we'll account for edge cases, like when the input is 0, where the result is simply 0. When handling edge cases, if the input number is 0, we can immediately return 0 as the base 7 representation. For negative numbers, we convert the input to its absolute value for computation but keep track of the negative sign to prepend to the result later. Once the edge cases are addressed, we move on to the main computation. While the number is greater than 0, we repeatedly perform division and modulo operations. The modulo operation, n%7, gives us the remainder, which represents the least significant digit in base 7. This remainder is appended to the digits list. The division operation, n//7, effectively shifts the number to the left by removing the least significant digit, allowing us to process the next digit. We continue this process until the number is reduced to 0, at which point all the base 7 digits are collected, albeit in reverse order. Finally, to obtain the correct order of digits, we reverse the digits list. If the original number was negative, we prepend a dash sign to the result. The last step is to join the digits into a single string, which forms the final base 7 representation. To optimize the algorithm, we handle specific considerations for edge cases and memory usage. For example, if the input is 0, we immediately return 0 without further computation. In terms of memory efficiency, instead of using a list and reversing it, we could use a string builder to construct the result directly, avoiding the need for an intermediate reversal. Let's walk through an example to see the algorithm in action. Suppose the input is 100. We start with an empty list for digits. First, we calculate 100% 7 equals 2, append 2 to the digits, and update n to 100//7 equals 14. Next, we calculate 14% 7 equals 0, append 0 to the digits, and update n to 14//7 equals 2. Finally, we calculate 2% 7 equals 2, append 2 to the digits, and update n to 2//7 equals 0. At this point, the digits list contains 2, 0, 2. Reversing it gives 2, 0, 2, which we join into the string 202. Thus, the base 7 representation of 100 is 202. The algorithm is efficient, with a time complexity of O log 7 n, due to the repeated division by 7 and a space complexity of O log 7 n, for storing the digits. For large inputs, the algorithm scales well as it handles numbers up to the integer limit efficiently. Let's examine the Python implementation of this solution. The function convert to base 7 begins by checking if the input is 0, in which case it immediately returns 0. For other numbers, it determines if the input is negative and works with its absolute value for the computation. It then enters a loop where the number is repeatedly divided by 7, and the remainders are collected in a list. Once the loop completes, the digits are reversed and converted to a string. If the original number was negative, a dash sign is prepended to the result. A few examples illustrate the usage. Calling the function with 100 outputs 202, and calling it with -49 outputs -100. This implementation is both clear and efficient, ensuring correctness across different edge cases. The process of converting a number to base 7 provides several key insights. First, the essence of the algorithm lies in repeated division by the base, where the remainders form the digits of the new representation. This principle applies universally to conversions for any base. Second, since the least significant digit is computed first, reversing the order of the collected digits is essential to constructing the correct representation. Finally, separating the handling of the sign ensures the algorithm works seamlessly for both positive and negative numbers. By isolating the sign logic, the core computation remains clean and focused on the mathematical conversion process. These insights not only help in understanding this specific problem but also lay the groundwork for extending the approach to other base conversion problems. Explanation of the code. This solution addresses LeetCode problem number 504, base 7 by converting a decimal, base 10, integer into its base 7 representation step by step. Below is a detailed breakdown of the code implementation. 1. We begin by handling the special case where the input number is 0. If number equals 0, the base 7 representation is simply 0, so we return it immediately. 2. Next, we check whether the input number is negative by evaluating number 0. If it is, we set a flag as -negative to true and work with the absolute value of number for the conversion process. This simplifies the logic for handling negative numbers. 3. To convert the absolute value of number into base 7, we use repeated division and modulus operations. Specifically, we initialize an empty list result to store the digits of the base 7 number, in reverse order. As long as number is greater than 0, we calculate the remainder of number divided by 7 using number %7. This gives the least significant digit of the base 7 number, which we append to result. We then divide number by 7 using integer division, number // equals 7, effectively reducing the number for the next iteration. For, after the loop, the digits in result are in reverse order, least significant to most significant. Therefore, we reverse the list using result.reverse. 5. We join the digits in result into a string using .join, result, to form the base 7 representation. 6. Finally, we check the is_negative flag. If the original number was negative, we prepend a dash sign to the base 7 string. Otherwise, we return the base 7 string as is. The solution is efficient, as the number of operations is proportional to the number of digits in the base 7 representation of the input number. This ensures that the function runs in logarithmic time with respect to the magnitude of the input, making it suitable for large numbers as well. This is the Java implementation of the base 7 problem, LeetCode number 504. The logic mirrors the Python implementation, with key differences such as using a string builder to build the result and explicit type declarations for variables. The method handles both positive and negative numbers, as well as the special case of 0. The conversion is achieved through repeated division and modulus operations, and the final result is reversed to ensure correct digit order. To begin solving this problem, we start with the example of converting the number 100 into base 7. First, we check for the special case where the number is 0. Since our input is 100, this step is skipped. Next, we determine whether the number is negative. Here, 100 is positive, so we set is_negative to false. Then, we initialize an empty list called result to store the digits of the base 7 representation, starting from the least significant digit. Now, we proceed with the conversion process. In the first iteration, we calculate 100 mod 7, which equals 2. We append the string 2 to the result list, making it 2, and then perform integer division. 100 divided by 7 gives 14, which becomes the new value of number. In the second iteration, we calculate 14 mod 7, which equals 0. We append 0 to the list, updating result to 2, 0, and divide 14 by 7 to get 2 as the new number. In the third and final iteration, 2 mod 7 equals 2, so we append 2 to the list, resulting in 2, 0, 2. Dividing 2 by 7 gives 0, so we stop the loop. At this point, we reverse the result list to get the correct order, which remains 2, 0, 2. Finally, we join these digits into the string 202. Since is_negative is false, the output remains 202. Therefore, the base 7 representation of 100 is 202. Now, let's look at the example of converting -35 into base 7. As always, we first check for the special case where the number is 0. Since the input is -35, we skip this step. Next, we determine whether the number is negative. In this case, it is, so we set is_negative to true and take the absolute value of -35, making number equal to 35. We then initialize an empty list called result. Now, we begin the conversion process. In the first iteration, we calculate 35 mod 7, which equals 0. We append 0 to the result list, making it 0, and then perform integer division. 35 divided by 7 gives 5, which becomes the new value of number. In the second iteration, we calculate 5 mod 7, which equals 5. We append 5 to the list, updating result to 0, 5, and divide 5 by 7 to get 0 as the new number. At this point, we stop the loop, as number is now 0. We reverse the result list to get the digits in the correct order, resulting in 5, 0. Then, we join these digits into the string 50. Since is_negative is true, we prepend a negative sign, making the final output -50. Therefore, the base 7 representation of -35 is -50. Lastly, for the special case where the number is 0, the function directly returns 0, as no further processing is needed. To analyze the time complexity of the function convert to base 7, we start by breaking down its operations. The first step is the initial check for whether the number is 0, which is a simple equality comparison. This operation takes constant time, or O1. Next, we determine whether the input number is negative, and if so, negate it. These are also constant time operations, so they do not add significant complexity. The main part of the function lies in the conversion loop. Within this loop, we repeatedly calculate the modulus of the current number by 7 and append the result to a list, followed by performing integer division to reduce the number. Both the modulus and integer division are constant time operations, O1, for each iteration. However, the loop's total number of iterations depends on the number of digits in the base 7 representation of the input number. For a number, the number of digits in base 7 is proportional to the logarithm of the number to the base 7, or log_7, number. This is the key factor that determines the loop's runtime. Now, considering the remaining steps, we have the reversal of the result list. Reversing a list involves swapping elements, which takes d time, where d is the number of digits in the base 7 representation. Since d is proportional to log_7 number, this step also runs in log_7 number time. After reversing the list, we join the digits into a single string using a string join operation. This operation also takes d time, which is again log_7 number. When combining all these steps, the most significant contributor to the overall runtime is the conversion loop, which operates in log_7 number time. This gives the function an overall time complexity of log_7 number. On the space complexity side, the primary factor is the storage of the result list, which holds the digits of the base 7 representation of the number. Since the number of digits is proportional to log_7 number, the space complexity for storing this list is log_7 number. Additionally, the final base 7 string that is constructed from the result list also requires space proportional to the number of digits, which is log_7 number. Besides these, the function uses a few auxiliary variables like is_negative, number, and base 7, all of which occupy constant space. These do not grow with the input size, so their contribution to space complexity is 1. Therefore, the overall space complexity of the function remains log_7 number. When compared to a naive approach for base 7 conversion, which might involve repeatedly subtracting powers of 7 to determine each digit, the optimized division and modulus approach is significantly more efficient. The naive method would require number iterations, resulting in a time complexity of number. In contrast, the current solution's time complexity of log_7 number is much faster, especially for larger inputs. In terms of best, average, and worst-case scenarios, the time and space complexity of the function are consistent at log_7 number in all cases. This is because the number of iterations in the loop and the memory required depends solely on the magnitude of the input number, not on its specific value or distribution. To understand this mathematically, note that the number of digits d in the base 7 representation of a number is determined by the logarithmic formula, d equals floor, log_7 number, plus 1. Each iteration of the loop processes one digit, resulting in d iterations, where d is proportional to log_7 number. As a result, the time complexity is log_7 number. Because the space used is primarily for storing these digits, the space complexity is similarly log_7 number. This consistent performance in all cases highlights the efficiency of the algorithm. When working on base conversion problems, there are a few common mistakes to watch out for. One of the most frequent errors is storing the remainders in the order they are computed without reversing them. Remember, the correct base representation is read from the last remainder to the first. If this step is skipped, the result will be incorrect. Another common pitfall is skipping edge cases, such as 0 or negative numbers. For example, 0 in base 7 is represented simply as 0, and for negative numbers, you'll need to prefix the result with a dash sign. Forgetting these can lead to runtime errors or incorrect outputs. Finally, be cautious about potential overflow or data type issues, especially in languages like C++ or Java. If the input value is very large, certain data types may not handle repeated division operations correctly, so it's important to ensure your implementation supports large numbers appropriately. Another common source of confusion is treating the base 7 result as an integer instead of a string. Base 7 numbers are often returned as strings to preserve characteristics like leading zeros or to handle non-standard bases. Misunderstanding this can cause incorrect results. Additionally, avoid performing unnecessary computations, such as repeatedly calculating modulo 7 for the same intermediate value. These redundant operations make your code slower and less efficient. Instead, focus on optimizing your solution by reducing the number of repeated calculations, which will help improve the overall time complexity. In an interview setting, base conversion problems test several important skills. One key aspect is recognizing the pattern of repeated division and modulo operations, which applies not just to base 7 but also to other bases like binary or hexadecimal. Interviewers may also introduce tricky edge cases, such as zero, negative inputs, or extremely large numbers, so it's important to clarify constraints and assumptions at the start. While it's fine to initially use a brute force approach, you should be prepared to discuss how to optimize your solution for readability and performance, particularly when handling very large numbers. Another valuable skill is extendability. Being able to explain how your approach can be adapted to other bases demonstrates a deep understanding of the core logic. For related problems, you might encounter tasks like converting numbers to Excel sheet column titles or reversing that process, which both involve similar base-like conversion techniques. Other related problems include converting numbers to hexadecimal, such as in LeetCode 405, which focuses on base 16. Of course, LeetCode 504 itself directly deals with converting numbers to base 7, making it an essential problem to master. Now, when it comes to alternative approaches, the iterative method, which uses manual division and modulo operations, is clear and intuitive. However, it can involve multiple steps and leave room for manual errors. The recursive approach, on the other hand, is elegant and concise but requires additional memory for the call stack, which can be a trade-off in certain scenarios. Finally, using string manipulation for the output can simplify handling leading zeros and negative signs, but it might add overhead due to the extra string operations. Understanding when to use each approach and their trade-offs can help you tailor your solution for both interviews and real-world applications. Thank you for watching. We reviewed the base 7 problem, explored the brute force approach, and discussed its complexities. Remember, mastering modular arithmetic and number systems is essential for tackling similar problems. Don't forget to practice, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!